Okay, so page 389, number 12. And so now I'm doing these, we won't use the negative on that equation, okay? Because we decided in class that making this video after we decided that in class. So number 12, the focal length of a convex lens is 17 centimeters. So F is 17 centimeters. A candle is placed 34 centimeters in front of the lens. DO is 34 centimeters. Make a ray diagram to find the location of the image. Well, right away, I know that the image should be 34 centimeters on the other side because look, DO is 2F. And when the object is placed at 2F, the image is formed at 2F on the other side. So here's my F, here's my 2F, here's my object, over here my F, my 2F. A ray going in parallel to the principal axis will get refracted in such a way as to pass through F on the opposite side. A ray going in through O will pass straight through. A ray going in parallel to the principal axis will get refracted so that it goes through F on the opposite side. A ray going in through O. Okay, where this one crosses, that will be the head. Where this one crosses, it'll be the feet. It should be the same size, equidistant. And you'll notice that I did cheat. Like I made a little mark on this ray where I knew it needed to cross at F. So I had something to aim for. Okay? Number 13. I could have used a ruler, but too hard with one hand. Convex lens of a copy machine has a focal length of 25 centimeters. 25 centimeters. The letter to be copied is placed 40 centimeters from the lens. So the letter is the object. And it's placed 40 centimeters from the lens. So it's between F and 2F, which means the image is going to end up being bigger, right? And it should be beyond F. So we're looking for DI. 1 over F is equal to 1 over DO plus 1 over DI. So 1 over DI is equal to 1 over F minus 1 over DO. So 1 over 25 centimeters minus 1 over 40. Common denominator is 200. So 1 over DI is equal to 8 over 200 centimeters minus 5 over 200 centimeters, which is equal to 3 over 200 centimeters. So DI is equal to 200 centimeters over 3. So DI is equal to 66.6 repeating centimeters. Okay, which is indeed beyond 2F, because 2F would be 50. Number 13 has a part B that says the machine was adjusted to give an enlarged object. And it's true, when the object is between F and 2F, the image is beyond 2F and bigger. Okay, how much larger will the copy be? So it's looking for magnification, DI over DO. DI, 66.6 repeating. DO was 40, so that's like 33.3 over 20, so 3.3, and then divide by 2, 1.6, repeating times bigger. So not a huge big difference, but 14, but probably about as much as a copier can do. Camera lenses are described in terms of their focal length. A 50 millimeter lens has a focal length of 50 millimeters. That seems to make sense. A camera is focused on an object 3 meters away. The object is 3 meters away. That's my DO. And with the 50 millimeter lens, locate the image. So 1 over F is equal to 1 over DO plus 1 over DI. So 1 over DI is equal to 1 over F minus 1 over DO. Now one of these is in millimeters and one is in meters. I'd probably change them both to centimeters. So it'll be 1 over 5 centimeters minus 1 over 300 centimeters. Common denominator will be 300. So this will be 60 over 300 minus 1 over 300, which will be 59 over 300. So then flip them. Di is equal to 300 centimeters over 59. So Di is equal to 5.08475. So notice how close that is to the focal length. So it's like it's treating the object, which is 3 meters away, as if it's a distant object. Number 4 says, or B says, 1,000 millimeter lens is focused on an object 125 away. Okay, so this time the F is, it is 1,000 millimeters. And the DO is 125 meters away. And so again, you're going to do 1 over F is equal to 1 over DO plus 1 over DI. So 1 over DI is equal to 1 over F minus 1 over DO is equal to, you could actually change the 1,000 millimeters to a meter. So it'll be 1 over 1 meter minus 1 over 125 meters. So 1 over Di is equal to 125 meters over 125. Whoops, meters goes on the bottom. Minus 1 over 125. So you get 124 over 125. And you get a Di to be 1.0081 meters. Number 15 says, solve problem 10 using a lens rather than a mirror. Okay, so number 15, problem 10 says a production line inspector wants a mirror that produces an upright image. If it's upright, it's going to be virtual. An upright image with a magnification of 7.5. And I'm going to put a negative on there because it's upright, so it has to be virtual. Okay? When it is located 14 millimeters from the machine part. So DO is 14 millimeters. So we can find our DI because we know magnification is equal to DI over DO. So DI is equal to magnification times DO. So DI will be equal to negative 7.5 times 14. So Di will be equal to negative 105 millimeters. But the question actually wants to know production wants a mirror. What kind of mirror would do this job? What kind of lens would do this job? It would be a convex lens. And then it wants to know F. So 1 over F is equal to 1 over DO plus 1 over DI. 1 over F is equal to 1 over 14 plus 1 over negative 105. Common denominator, I think, is 210. So 1 over F will be equal to 15 over 210 minus 2 over 210, which will be 13 over 210. So F will equal 210 over 13. So F will end up equaling 16.154. Last one. See if we can do it before we run out of time. A convex lens is needed to produce an image that is 24 centimeters behind the lens. An image 24 centimeters. That is 0.75 of its size, so magnification is 0.75 times. And it wants to know what focal length should, so again you can find your DO. DO from magnification is equal to DI over DO. DO will be equal to DI divided by magnification. So 24 centimeters divided by 0.75. DO should end up equaling 32 centimeters. Okay, and so then you want F, 1 over F. We're going to run out of time. The answer is 16.